Okay, welcome to this tutorial where we're going to look at acid to base equilibrium. Now we have the first question that says, what is the Arrhenius definition of an acid? Give an example of an acid according to this theorem. So the Arrhenius definition of an acid is that an acid is that dissociates, going to dissociate to produce hydrogen as only positively charged ion. So examples that we can give, there is hydrochloric acid. This one is a very good example. However, we can also give sulfuric acid. I think that one is okay, but you can just give hydrochloric acid in this case. Okay, so that's the Arrhenius definition of an acid. It says that an acid is a substance that dissociates, or rather dissolves, or it dissolves in water to produce hydrogen ions as the only positively charged ion. So that's the Arrhenius definition of an acid. Then we have the Arrhenius definition of a base. So the Arrhenius definition of a base is that a base that ionizes or dissociates, like we said in the previous question, that ionizes in water, negative charged ions. So that's the definition of the base according to the Arrhenius definition. So an example we can give here is sodium hydroxide. This one is okay. So we can give that as an example. Yeah, because of the hydroxide part. So when sodium hydroxide dissociates in water, it's going to give us oxide ion, which is negatively charged, which is also aqueous. So that's what happens. By HCl there, we mean that we have a hydrochloric acid is equal to hydrogen ion. Everything is aqueous here. So this is what we're looking at, and here we have that. So we're done with the Arrhenius definition and giving examples. Now we go to the Bronsted definition of an acid and the base. So the Bronsted definition of an acid and base is a concept of conjugate acid to base pairs. So here we'll be talking about conjugate acid to base pairs, which is defined as an acid, its conjugate pairs with its conjugate there. Okay, so that's the Bronsted-Rary theory definition of an acid, of acid and base. So it's about the acid is what we're talking about. Yeah. So let's go to the same question now too, where we're told to identify the acid, or identify base, conjugate acid, and conjugate base for each of the following reactions. So so we have the first reaction or chemical equation, this one plus that and that, giving us those things. So here, what happens is that if you have an acid, we need to get the conjugate base. This should give us a conjugate base. Let me just use letters to identify those instead of writing in full. Okay, so if you have an acid, we're getting the conjugate acid. So the question is, how do we get those? So the acid the acid should give us a conjugate base, and a base should give us a conjugate acid. So how do we get to a conjugate base from an acid? So here what we do is we remove one hydrogen ion. So we move one hydrogen ion. But from a base to conjugate acid, we add one hydrogen ion. So this changes even the charge. In case maybe A had no charge, but you remove one hydrogen ion, the charge will be negative because of removing minus. So there's that minus. But if it's a base and you add the conjugate acid, we're going to have a plus positive charge. So for instance, in this case, if we look at this one, it's having a hydrogen, but that side is not there. And the charge has gone to negative. So then that means we know that this is an acid and it has changed into a conjugate base. So because the hydrogen has been removed and the charge, it was from 0 to -1. That's by removing 1. So that's the idea. And we have this one. Since this is an acid, this one is going to be a base. So on the reactant side, we are going to have acids and bases. But on the product, these are conjugate acids, conjugate bases. So now, so from the base, we get the conjugate acid by adding one more hydrogen. So here we have H2. If we add one more, it's going to be H3. So which means that this is the conjugate acid. So the conjugate acid coming from the acid. So that's how we do such calculations. So let me just give you an example. Let's say we have sulfuric acid like this. So this is an acid. How do we get a conjugate base from sulfuric acid? So we'll remain with just H, then SO4. So you just focus on H. Don't look at anything else here. So because we have removed one hydrogen, this is going to be to the power negative, because there it was power 0. It had no charge, so it will have a charge of negative because of the removal of one hydrogen ion. So that's what happens. And then if you have this as a base, let's say we have SO4. We can even put just for trying. Let's say this is the base that we have, and we want to change it to a conjugate acid. So, if this is an acid we have, so this we're changing to conjugate base. Now let's say we have a base, we change it to conjugate acid. We're going to add one more SO4. The charge also adds. We're going to add one more charge, so it will be 2 positive. So that will be the conjugate. We have acid and base there. All right, I'm pretty sure that has at least shifted your understanding. Let's look at this one. Oh, it's giving us that. So what has happened there? H2 has been moved to H1, and the charge is negative, meaning that there was a removal of hydrogen. So this is clearly the conjugate base. If that's the conjugate base, then this is the acid. If this is the acid, then the next one is the base, and this will be the conjugate acid. Because previously, when we have hydrogen and it changes to, when we have water and it changes to hydronium, so that's the conjugate acid. Take 1 minute to do it, so you can pause the video and do it right now. All right, so you can confirm your solution with what we're going to find together. So here, if we look at this, there's a hydrogen there, but here it's not there. There is no hydrogen, there is no. So what do we do in this case? So because the charge here is negative, so this is just for typing. I just copied it from PDF to this form. So now we have that negative charge there, which means that a hydrogen has been removed, like one hydrogen. So that means that this is already the conjugate base, and that means that this is an acid. So therefore, this is the base. And since we didn't do this in the previous example, we can be doing that just to make sure that you're okay with everything that is happening. Okay, so define the terms Lewis acid and Lewis base. So a Lewis acid is a proton donor, and a Lewis base is a proton receptor. So that's the Lewis acid and Lewis base definition. Donor. These are those who donate, and is receptor. Okay, so a Lewis acid is given by OH negative. So that's the Lewis base and acid definition. Now let's draw a dots and crosses diagram on a molecule of aluminum chloride, that is AlCl3, showing outer elements electrons only. Would you expect this to behave as a Lewis acid, Lewis base, or neither, or both? Explain your answer. So what we have here is we have aluminum is found in group 3, in group 3. So therefore it has 3 electrons in the outermost shell, because we're only showing the outer shells, outer electrons. So then let's put in the chlorine there, chlorine. So here we're going to have, because chlorine is in group 7, this has seven electrons there, like that. So when we add these, well, what's going to happen? So there'll be a sharing of electrons. So a sharing of electrons is going to take place. Is going to take place. Yeah. And how will this sharing be done? So the sharing will be like this. So we're doing this because we're trying to identify it in terms of acid bases or neither. We have to work it out in this way. So we're going to say this is going to be, we have aluminum, one, there'll be that sharing. Oh, it was a dot and a cross diagram. So we can just change for the aluminum, since it only has 3. So we have dots there. So here there'll be that dot, and then we'll have this. So there'll be that kind of sharing. So electrons are going to share. So when that happens, here we have chlorine, remember, and chlorine there. So that means that if this one electron shares with that, we have 6 more electrons outside. And here also we'll have 6 electrons, and there we'll have 6 electrons. Yeah, something like that. So this is how the compound is going to show. Now, if we look at chlorine, you find that it's got 1, 2, 3, 4, 5, 6, 7, 8. It's balanced. Even this one, all of them are balanced, but aluminium is not balanced because it's only having 1, 2, 3, 4, 5, 6. After sharing, it's now having 6 electrons. But in actual sense, it's supposed to have 8 electrons. So what's happening there is that aluminium needs 2 more electrons. So aluminium needs 2 more electrons for it to have a full outer shell like chlorine. So therefore, what we are going to, because of this, that means that aluminium, that means that this compound is expected to be this compound is expected to be a Lewis. It's expected to be a Lewis base. Yeah, it's expected to be a Lewis base. Yeah, so this one is a Lewis base. Why is it a base? Because it's having a charge of 2 negative. Yeah, so that's why it's a base, and therefore it's expected to be a Lewis base. If the charge was positive, we say that it's what is. It's a Lewis acid. Okay. So explain your answer here. We're saying that it's because it needs 2 more. It needs 2 more ions, or rather 2 more electrons, for it to be fully stable. So the outermost shell needs 2 more electrons for it to be fully stable, because it's got 6. Okay. Yeah. So we go to the next question. So we have to calculate the pH of 0.01 mole per liter acetic acid with a Ka of 1.8 times 10 to the power negative 5. This is to the power negative 5. So how are we going to do this? So first of all, we need to show this how this process is done, how acetic acid dissociates into the component, into its components, because we said it's going to be dissociating. So what we're going to have is something like this. We're going to have CH3 COOH. This is in aqua state. So this is going to give us what? So when it dissociates, we're going to have hydrogen. So we remove one hydrogen there, and this is aqueous plus COO. So now it won't have the, so because the hydrogen was removed, it's going to be negative there, and we have the aqueous there. So that's the reaction that takes place there. Now, now here, what happens is that at the beginning, we have what we call initial molarity. So that's the molarity or the concentration. So the initial concentration here is 0.01. And the initial concentration for this, we don't have it. So it's going to be 0. And the initial concentration of this is not there also. It's going to be 0. And then there is what we call change. So the change is there in terms of balancing. We haven't put any numbers. So this is going to be negative x because it's going to be reducing while the product will be increasing. So here it's positive x. And then we can have now equilibrium. What's the equilibrium concentration? Here it will be 0.01 minus x. And this will be just x. And then this will be x. So how do we get these values? What we do is we add what is there. So here of 0 plus x, 0 plus x, and 0.1 plus negative x. And that's how we have those values. Yeah. So now, what we are going to do is the Ka is given by, so the Ka is given by, so it's more like we have the equilibrium constant, the equilibrium constant for dissociation. So the equilibrium constant is going to, first we consider the product, which is of this 3H acetate, the concentration of the acetic acid, like that. Okay, so now that means we have what? Power negative 5, and this gives us, so the concentration of H high, so H ion is that, so we have X, then also X over that is now 1 or 0.01 minus X. So if X is very small, let X be very small. That means we're going to have 0.01 minus X is just 0.01. So we're going to, instead of using this for the denominator, we'll use 0.01. That means that now we have 1.8 times 10 power negative 5 is equal to x squared over 0.01. We make this and cross multiply. So x squared is 1 times 0.01. So what will that give us? To give us 1.8 times 10 to the power negative 7, I think, just so 1.8 exponent negative 5 times 0.01. Yeah, so this means that x squared is 1. To find the x, we square root both sides. That means x is equal to the square root of answer there. It's 4.2426. So that is the value of x. So now, because this is acetic acid, that means it's got the Ka. So Ka is the equilibrium constant of an acid. So that means to get the pH, we're going to say, so pH of hydrogen or hydronium ion, this is equal to negative log. So, oh, I didn't finish this one. It was times 10 power negative 4, times 10 power negative 4. So we add log to this. We're going to have 3.37 with a negative. So the pH is going to be 3.37. So that's the pH value of that one there. So I'd like you to pay quite some good attention as we do the next one, because this one is starting to have the Ka, like in the previous case. Now it has the Kb. So we have ammonia. So the question is, what happens to ammonia? So we're going to react ammonia in water. We're going to dissociate ammonia in water. So we'll have NH3, which is going to give us what? So here, because this is ammonia, we treat H2O as the acid. So ammonia is a base. No wonder why we treat water as a base. Remember in the previous case when we were doing the Lewis acids to base, not Lewis, but Bronsted theory. When we were applying that, we found that the water there was a base, and we had to get a conjugate acid. But because ammonia is a base by nature, water here is going to exist, or rather behave as an acid. So what would be the conjugate acid of ammonia? Since it's a base, we just remove the hydrogen there. Since we are going to make it as an acid, the conjugate acid, so we're going to add one more hydrogen, so it will be NH4 positive, which is just ammonium ion of OH negative. So this is the conjugate acid, and this is the conjugate base, and this is the acid, and that's the base. As simple as that. So now we want to, so remember, water is liquid there. I wanted to make sure I stress that point. So water is liquid there. So we don't have to even pay attention to it, because a liquid, in terms of equilibrium, it has a what-is of 1. It has an activity of 1 in thermodynamics. So there, what we are going to have is we have initial concentration, then we have change, and we also have equilibrium concentration. So the initial concentration is 5 mol per liter, so it's 5 mol, and the change is always x, because here we don't have any stoichiometric coefficients, and this is the initial concentration of water. So there's no need to pay attention to this, and because these are products, they're going to have 0, 0 each, and then so this is negative x and x, because those are products. So the change is going to be 5 minus x, and here we have x, and there we have x. Yeah. So now 5 minus x, I'm sure it's clear. So now we go to the next stage where we have now to find the what-is. So here our Kb is given by what? So Kb, yeah. So Kb is going to be given by, so why we're having Kb is because the same ammonia that we have is a base, so we can't get the Ka. So here we just get the concentration, positive, negative, and concentration. And like I said, water, so there's no need to put it. So I just don't want you to be confused. I want you to be clear. So the activity of water there is H4 post over 1 times is just going to be NH3. That's why they rarely put water there. It's rarely put, because there's an activity of 1 in thermodynamics. So now we have the value for the Kb. The Kb is 1.8 times 10 power negative 5, which is equal to the concentration of ammonium is ammonium ion is x, multiplied by that of hydroxide is also x, over the concentration of ammonia, which is 5 minus x. So now here, because x is very small, we assume, so this is always an assumption, we assume that x is very small. So we're going to say let 5 minus x be equal to 5, meaning that x is literally very small. So we're going to have 1.8 times 10 power negative 5 is equal to x squared over 5. So make this over 1 and cross multiply. So x squared is going to be 5 times 1.8 times negative 5. So this will give us 9 times 10 power negative 5. So we square root both sides, which means x is going to be, so the square root of answer is 8 6 times 10 power negative 3. So once you reach here, we're going to find now the pH. So because you have said find the pH, first of all we get the pOH. So here the pOH, because we have the Kb, so the OH. So by OH we mean that this is a base. So what we are going to have is that pOH is equal to OH6 times 10 power negative 3. So the negative log of that is actually 2. So this is going to be 2.023. Now, because yes, we find the pH, not the pOH, what we are going to do next is to say that at 25 degrees Celsius, so at 25 degrees Celsius, at plus pOH is always equal to 14, because the pH scale is written from 1 up to 14. So the pH plus pOH, the total should be 14, which means that now we have pH plus 0. Just like this. Okay, so we have 2.023 equal to 14, which means that pH is equal to 14 minus 2.023, which is 14. So this is going to give us 11.98. 11.98. So that's the pH of this. So by that, it's really true that it's a base, because bases start from 7. A pH of more than 7 is a base, is a pH for a base, and a pH value of less than 7 is a pH for an acid, and a pH of equal to 7 is a pH for a neutral solution. Okay, so find the concentration of the hydroxide ion and the hydrogen ion, and the pH of each of the following. So if we have this, we're going to say 1.C at this is going to be what? It's going to be K positive plus CO negative. So it's going to have those ions. So because this is just 1-to-1, then this also, so all you do is just multiply with the stoichiometric coefficient, you multiply that. So which means that the concentration of the hydroxide ion, we get that one with the negative charge ion, which in the concentration of the hydrogen ion is again 1.0 m. Yeah, and then now we get the pH of this is going to be negative log of the hydrogen ion, which is, so the negative log of this is going to be the negative log of what? Of 1.0, and that's what, so the log of 1 is 0. So this has a pH of 0. Yeah, it's good, a pH of 0. So then what is the pH of the other one? So the pH of the hydroxide ion, pH of the hydroxide ion is going to be pH pH of the hydrogen ion minus, it's going to be 14 minus that. So it's negative plus 14. That's just going to be 14, something like that. Yeah. So there's no need to find the pOH. Okay, so the same applies to this Kf. You just have to know how it's going to dissociate. So this is going to dissociate as, so fluorine is in group 7. So this means we're going to dissociate this as K positive, potassium aqueous, and even this one aqueous. So now after you do that, then you say, so because here we have 1m, even this is 1m and that is 1m, unless there's a 2 there, that's when you multiply that 2 with the m's. So that means that the pH will be just like in the previous, which is what? 0. This is for the other one will be 14. This is for the hydroxide ion. So we're going to stay at 25 degrees Celsius to give us what? 14. So if okay, so all right, I think we don't have to do that. So you just say that the other one will be 14, just like the way we have calculated in the previous question, so that we can do the other question. So the other question says arrange the following, that is 0.1 m solutions in order from the most acidic to the most basic. So what's happening there is that every solution here is 0.1 m. The concentration is 0.1. So what we have to do here is we have to identify solution in terms of whether they are basic, acidic, or neutral solutions. Are they salts? If it's a salt, we have to tell whether it's basic or acidic. If it's not a salt or it's acidic, like this one, some of these we can already see, okay, this one is an acid, like this. So those are acids, those two. Because we start with the hydrogen. There's a hydrogen ion there. Yeah. Okay, so let's start with this one. So we have CaBr2. How can this be? And what? 2Br negative. So that means this one is neutral. So this is a neutral salt, because this is a salt and it's going to be neutral. Yeah. When we get the other one, this is also a salt. It's into K positive and NO2 negative. So because of the charges are similar, like they all have the same charge. Yeah. So this is basic. This is basic. That just like in the case of sodium hydroxide, so we have any positive charges are just the same. So that's basic. So this one is basic. And we have the next one, which we have already said is an acid. The only thing we have to tell is whether it's a strong acid or it's a weak acid. So the next one is HCOClO4. Yeah, so this is a strong acid because it has the highest number of oxygen. So those acids we call oxyacids. So when when oxygen is present in an acid and the watt-cis of oxygen is high, then that acid is very strong. So this is a strong acid. This is a strong acid. Okay, and then the other one also is we also have this NH. Oh, it's H. In terms of hydrogen, we have just 2 watts. So we can take this one as weak. So this is a weak acid. This is a weak acid. HOCl4. So this is a salt. But the question is how are we going to dissociate this one? So this one will dissociate into ClO4 negative, just like in the previous, then everything else together, which is a positive. So this is an acid. This is an acid. And when we look at the oxygen that is there, there's more oxygen. So this is also a strong acid. Okay, so to arrange these in order from the most acidic to the most basic, we're going to start with that same one, the strong acid. So we're going to, and then the next one will be the same one, this. Or let me just put the numbers. This will be 1, 2, and then 3, and then this is a base because this is a base and that's neutral. So 4 will be. So this will be 4 because it's neutral, and the last one, number 5, is this one because it's a base. Yeah. So we have this comma HONH3, CaO4, comma HNO2, comma CaBr2, comma KNO3. Okay, so in that order, yeah. So they also asked the question to say, we were 0.10 m solutions of the following sorts be acidic, basic, or neutral. See appendix 5 in zoomed values. So I tried to check for these values, but I think I don't have zoomed here. There's another book that I use for studying this, although it doesn't have those values. But when you go to appendix 5 in zoomed, get the Ka or Kb values, and then we are going to be applying what we did here, what we're doing here, this kind of, okay, this one, okay. So right, this is what we are supposed to apply to get answers to that particular question. Yeah. So, or maybe if you found them, you can send me, and then I can, or just send a picture. Yeah. Then I can come up with answers for you for these. All right. So for now we can end here, and then we'll do some more later on. Okay. So I hope you enjoy the day and you enjoy the solutions. Yeah. And subscribe to the Power Excellence channel, YouTube channel. That's where you find great content. So the reason why we want you to be subscribed is so that you are able to know whenever we upload any new content, and kindly share to other people, because we want to always reach out whoever is having challenges in solving tutorials or assignments or whatever you're doing. As long as it's academic and it's concerning sciences, we're there for you. So enjoy the day. Thank you.